Safe Software is pleased to present the 2009 FME International User Conference. This session is presented by Michel Gilbert, a project manager who has been with the Center of Topographic Information for 20 years. Michel is in charge of development data acquisition projects, GDB database, and metadatabase, and his experience with FME dates back to 1998.
Good morning, everyone. Thank you to come to my presentation. It's been classified as an advanced topic, although the idea of to design single workflow workspace is to have easy workbench. So we'll see what. So I'm working at the Center for Topographic Information. We're the national agency for topographic information in Canada. So we produce different products, such as what you see on GeoGratis, like the NTDB for the National Topographic Database, the CanVec, which is the new vector product, the Toporama for the web mapping, and the CanMatrix is georeference maps of the topo maps. And also we're part of the GeoBase project. It's a partnership with the provinces and the federal government. And the main products are the road network, the hydrographic network, the CDED, the elevation model, and the ortho image in Landsat 7 and spot images. So at the high level of our geospatial environment at the center, we have the database, the enterprise database, the GDB, which is the geospatial database, and the GeoBase database. And also at the metadata, we follow the FGDC and the ISO standard for metadata. At the dissemination level or the distribution, well, we have it's how we produce our products and also the web mapping. For the data acquisition process, we have different processes that produce the data, and most of the work is done by contracting out the work. My presentation will address more the aspect here of how we validate the processes here using data quality specs that are derived from a catalog that I will explain a bit later. And the data aspects are used by internal teams and also by the contractor. So we use FME since 1998, as I remember, maybe a bit longer than that. At first, we use it for data conversion, so the COGIF format. That was the way we manage the data at first on files. And then we use FME to load the data from files to the Oracle Spatial database. And after that, we start using Spatial Direct for the online data distributions and also for web mapping. In the production environment, we had the laser scan system running on the VMS platform. We're still using it. And we use a QLF format, which is the format we use to communicate or distribute the data with the contractors. And then we start participate in the GeoBase project, and we get more complex data, network data, and the LRS for a linear reference system. So we work with Safe Software to develop a transformer that can move from LRS to simple vector data. And then we use FME for raster. And in the new environment where we use the ArcSDE and ArcMap, we decided that the main application that will be used for processing would be FME. So in our organization, we say when you have a task to perform, you try with FME. If FME cannot do it, as safe software if they can improve the product and or have new transformer to help us. So basically, most of the work is done with the safe FME. So what we realized since we start using FME in 1998, we use it for loading data. Then today it's more for transforming the data and also to validate. At this time, we had more than 600 workbench in the data acquisition and data management, and more than 45 custom transformer, and also 90 workbench for the data distribution. And we have many builds that we still use because we have processes that may last 10 years, and we don't necessarily synchronize all the workbench to be conform to the last build. So we have to keep many versions of FME on our servers. So the idea of to design a single workflow workspace came from the maintenance purposes first, because how to support the workbench that other people develop. As you know, with FME, it's easy to build a workbench, but it could become very large and hard to understand. So the idea was to simplify solution. So to have one task and one workbench. You not try to resolve many computing in the same workbench, and also to try to reduce duplication. With FME, you may have a problem to solve that may be similar to another one that you've done before. So many times what you do is you just copy this and you start from the other one and you duplicate workbenches. And it becomes very hard to maintain after all. And also we wanted to share solutions. So we have many processes, but many processes do the same task. And what happened is for the different projects, they have their own workbench that they were doing the same, almost the same work. So the idea was to try to build FME or workbench that are good for many processes. And also at this end, we were at the time with the new environment with ArcSDE and all that, we wanted to implement our concept of data quality or data validation. So basically, design single workflow is best practices that we built with years, and the idea is to design workspace that perform specific enterprise tasks, whatever the data source is. The idea is to get the data independent and also easy to maintain. So the design workflow workspace, the single workflow workspace, came from a presentation I attended the last FME user conference by John Snell. It was about design patterns. So the idea was to have one single entry for all the sources, and also at for the destination was to use the fan out and use a filter to get the output. And at the central workflow pattern, the idea is that for one task, we want to develop one custom transformer. And also we decided to design rules for a custom transformer. What I mean by design rules is more programming or best practices of how to build custom transformer. And the last point, it was how can we get the source independent of our quality rules. I will explain that. Okay, the designing rule or the programming for a custom transformer that we asked the programmer or the user FME to do is to self-describe the input-output pipeline. allow parameters. So what we want, if we want to make sure that the custom transformer is independent, so we use parameters or variable to get the information passed. We also group the output by names and different output, I mean. And what we want, if we want to make sure that all the feature that goes in the custom transformer will go out. We want to make sure that if they're unprocessed, there is a pipeline that will say unprocessed features to make sure that at the end, when we do something else with the data, we know we have all the data at the output. And also to clean all the working attribute that was that was done in the custom transformer. And then to make sure that the custom transformer is data model independent, so we do not pretend that the source or there are attributes that things that be there when you get in. So we want to make sure that we don't use attributes that came from the source. So I talked about the single input source, the fan out, the workspace, the central workspace. But the main idea was to get the data quality rules applied to them. So our data quality or validation is based on the standard ISO standard and how to measure the quality. And the basic of the different quality concepts are for geometry and different for attributes. And the results are, we have classes, feature classes that get output the result for the contractors or also for operators that will correct the errors. And the data validation principles are expressed in the catalog. The catalog is a dictionary of information about the features. So it's descriptions or the properties of the features and also the rules or validation rules or quality rules for the features. So the catalog is kept in a database and we can derive specification from it. So this is the catalog of all the features of the GDB or Geospatial database, the enterprise database. And we can derive from an application an XML document and publish it in HTML. For each project or processes that start a new product, they will inherit the master catalog and will adjust it according to the project. And again, we'll get an XML document and HTML, and that become the specification for the contractor and also for the team at the office. We have script that derive SQL script and to generate database tables. So the way we keep or work with the validation rules, we use tables. This is an example of the catalog. So you have an entity or feature, which is the contour. In this, that the attributes or properties of this feature. We have subtype, like in this case, we can see it's a contour or something, the depression, I think. And also for this feature, all the data quality principles are kept here. So as I said, from this database, we generate the XML document, and then we generate the tables that will be used for the different workbench or the custom transformer. So here an example of a principle, a validation rule to validate the attribute domain of attributes. So here you have an attribute acquisition technique, and we use the regular expression to validate what are the domain available for this. At the level, at the database table, but you'll have the same information transported there. Here another example, but this time it's for a spatial constraint. I will explain that a bit later. So here the first example of the FME to validate the attribute domain for features. So the idea is this is a rule that is included in the catalog, and we express the principal use the regular expression to validate the domains. So we built a custom transformer that will allow parameters. And the FME transformer, the main FME transformer that we use is the string searcher for that. We use the regular expression to validate the value that are of all the elements. And the output will say if it's fail or it's passed. And when you have your custom transformer, now you can build your workspace for the source you have, and also you can get the result. So here the example. So you have a source data that has a different attribute. One of them has to be the key or the primary key, how you will link the rules of the validation with all the features. So here from your table of validation, you can make a join. The join here, or it could be an SQL executor or a joiner, and you link the validation rules for each feature using the code specs of your features. So one feature may have many rules, and that's why we use a list. So the list here will be the input of the custom transformer. The validation will be performed, and then the output will have from the fail channel all the errors that was catch. So, and the idea of the design is the same thing for all the concept of validation we want. Like here we have the source, we have the parameters that are passed as the feature parameter, and we have the joiner here, and this is the domain transformer, the custom transformer for validation, and all this is how to manage the errors that was found in the custom transformer. Okay, the other one I wanted to talk about, I still have just 5 minutes, so the spatial constraint validation. So the idea is to validate the relation between geometry. So we use the 9 intersection matrix. So it's the Eigenoffer or Eigenoffer concept. So I'll go. I wanted to explain how the 9 intersection matrix was working. But in this example here, how do you want to express the intersection between two lines? So using the 9 intersection matrix, we can have the value here of Eigenoffer, or the representation is this representation here. So there are many predicates, that's what we call them, crosses, overlaps, contain, touch. So we have 21 different predicates that we use to validate all the relationship between the geometry of the features. It's a big task to build the catalog. You have to check all your features and compare all the relations you want against all the features. So it's long to build, but once you've built it, but we just have to keep them in the catalog, and it generates. So the idea here. So I'll explain for the constraint. So the same thing here. We have a source. We have the joiner. And we have the custom that we build to validate the relationship between features. So here is an example from the catalog. So we want to check if a built-up touch each other. It's not supposed to. So again, with the joiner, with the feature, and with the table of all the constraint, spatial constraint, we build a list of all the constraint to validate. And the result will be similar to the one we've done for the attribute domain. So to validate all the relation between the geometry of all these features here, the workbench looks like that. I mean, it's very easy to maintain and understand. So the only what we have, you have features, you have the joiner that join with the tables that contain all the constraints, and we pass. It becomes a list of the features, and the custom transformer will validate all of them. To summarize, while single workflow workspace is based on best practices, really, and it was the way to use the data quality principle that we have at the office, and we use custom transformer to build them, and we use them for data validation. For the future work, but you can see the concept could be applied for generalization principle. There are different parameters to describe this different concept of generalization. They have to develop custom transformer, and instead of doing validation, we'll do transformation of the features. Thank you.